Okay, let's get started. Okay, last time there was a little glitch in demo. So let me finish what I have started. So I'm trying to explain, right? I'm trying to explain Zynq 7000 device, right? Zynq 7000 device. And I was trying to explain the major component inside this PS section. Okay, Zynq 7000 device. Okay, it's composed of two, big part. First one is PS, processing system, and PL, right? PS, it is fused, hard macro. In other words, fused into the device. So you cannot take it out. It is always there, right? So there are two CPUs, IO devices, memory, on-chip memory, right? And cache, memory interface, and so on. Okay. And PL section, you can design, you can download, you can design your hardware, custom hardware from your computer. Okay, and download it to this section, PL section. So this PS can interact depending on the function of your custom logic. PS can interact with PL. Okay, and then we were here, right? So I told you, right, when you have a new device, right? So I told you a story, right? Last time you are working. Assume that you are working for Samsung, right? Your boss passed you a hardware system, okay, PCB system, where is some unknown hardware component mounted. Then what do you have to do, right? And your boss also passing you hardware specification of the device, that unknown device. Then what you have to do is you read that document, right, and figure out what kind of hardware component that unknown device has, and then you have to figure, okay, it has CPU, IO devices, and memory, right? And the next thing you have to figure out is this one, memory map. So what do you have to do? You are writing, your job is writing software, right? Then you have to figure out, memory map. Okay, my IO device, for example, UART. Okay, my IO device. Okay, many IO devices. UART is located from this address to that address, right? Memory map, right? And then USB is located from the first start address to end address, right? Base address to the end, right? And so on. So you have to figure out that memory map, right? To touch IO devices and memory, right? To load your program into the memory, right? So I was trying to show you, right? It has two, okay, Zynq 7000. Zynq 7000 has two, okay, master interface. Is this one, the two down arrows, right? Two down arrows. So master component, that means your custom hardware, custom logic, supposed to be slave, right? Master slave, right? Masters. So once you download, once you have your custom hardware located in PL, then memory area. Someone should assign memory area, right? Like this. Someone should assign memory area like this, right? You are to start from these two, that end address. USB, this one to end, right? And PL, right? The custom hardware you are going to download will be assigned within that memory area. So it is 1 gig actually, right? If you do a little math, right? 4 7 zeros to 7 episodes, that is 1 gig, 1 gig space, 1 gigabyte space, right? And this one is next 1 gigabyte space, right? I think I draw, right? I draw memory space diagram. So let me do the demo. Okay, I'm trying to allocate IO device to here, that connection. Okay. 4, 8, right? Remember 4 and 8 other address. Trying to connect my IO device to this left arrow, down arrow, and also, right down arrow, right? That connection. I'm trying to show you a demo because it is boring to just follow the PowerPoint, right? Right? Right. Dongwon is already sleepy, right? Boring. So that is why I'm trying to show you a demo. Okay, so okay, cancel the last thing. I figure out what the problem is. So last time I did TMP, I think. So it is block diagram based audio design, right? Vivado is providing this nice GUI environment. You can use, block diagram based schematic, very high level schematic based hardware design. Right? So there is a choice. If you don't like it, you can design Verilog, right, from scratch. Okay, you don't like this block diagram? That's okay also. Okay, let me remove everything, right, just in case. So what I can do is remove everything. PS also, everything. Okay. Then, okay, add a new one. Zynq, PS, right, PS, processing system. PS and PL, two part, right? And then just run block automation, then it will, depending on the default setting. Okay, what do you mean by default setting? The default setting of this PS. Okay, Vivado has default setting, meaning which IOs are enabled, right? And which connections are open, right? Those default setting, right? So based on the default setting, it is trying to, show you the block diagram. Okay, so that is default setting, and the connection on the left, that is input, right? Input and output, input and output. So by looking at this TTC, okay, I don't think we need TTC. That is actually triple timer counter or something like that. So let's remove because it is not. Okay, there is no TT. Where's this one? TTC, triple inside application processing unit timer. Not this one timer, but you have watchdog timer. I think 3 of them TTC. Yeah, I think so. So to turn off triple timer counter, you can do MIO configuration. Yeah, application processing unit. You get this timer, right? Uncheck this. Okay, then that disappears, right? So for now, look at this. M master, right? M means master XC GP0. Master connection, right? Master XC Amba Protocol. Amba. So interconnection protocol between master component, slave component, master and slave, right? right? Proprietary protocol. And then what? GP0, general, I think general purpose zero, number zero. I don't know what the acronym is, but GP0. So that is only on, right? That connection, meaning that connection, the left down arrow, that connection, GP0, that is on. Okay. Then what? You want to add some simple, very simple I/O component called GPIO, right? GPIO is the most simple, most really simple, hardware component, right? You can design GPIO from with Verilog in 1 minute, I think. Okay. If you are quick in typing, then you can design it in 1 minute. Very, super simple IO component. General purpose, right? You can connect anything to this output. Anything, meaning something like examples are what? LED, switch, right? 7 segment, right? Those things. So we have master connection. Okay, here. Okay, let me. Okay, master connection M and slave XC, right? XC connection. Then tool is offering. Can I make connection? Run connection automation. Yes, right? So select, right? Select everything. Then XC GPIO, right? XC GPIO 0, XC GPIO 0, output, right? Output and input, slave input, right? So you can make connect, you can probably select. Then it is offering. It is offering what kind of options you have, right? Like this, some options. Okay, some options, not many options. Master interface in our case, which master interface? Okay, do you want to connect that slave to? Okay, so in our case, we have only GP0, right? So no choice, right? But if you have two, let me open one more master connection. Okay, here, where is that? PSPL, okay, PSPL. This one, master. Okay, for now, GP0 only checked. So check. Okay. Then second connection, right? Second connection appears. Okay. And then if you are trying to make connection with this one, then select, this one. Slave should be connected to which master? Oh, here, sorry, here. Here, GP0 and GP1. Okay, GP0, GP1. So you can select GP1. Okay. Okay, so tool, right? Tool is already made that connection. Look at this, right? Slave, this one, it is going through this XC interconnect module, hardware module. Then important thing is this one. From PS GP1, okay, line is coming out from GP1 to here, slave connection in interconnect, right? Slave. Then this interconnect connection module also providing master interface, right? Master to slave. So essentially, the GP1 is connected to that slave through interconnect. Right? So you don't have to worry too much about this interconnection module. Right? Then we have it is offering one more connection, run connection automation. So why? Because that is open. Which one is open? Input is open. This input. So if you think about hardware design, input should be connected all the time, right? You have some hardware component, digital logic, input, right? Input and output. Then output is not connected to anywhere, then that's okay. It is not connected, it's okay, right? But input is not connected, then what would happen? It is floating, right? You don't know it is 0 or 1. You don't know, right? It is floating, right? So then that input could be propagated inside, this logic. I don't know. I'm cooking up, right? Inside this hardware logic. So unknown, right? Unknown. Then unknown is propagated. Then output is unknown. Then unknown, right? So the input should be connected all the time. Otherwise, you run into some problem, right? That makes sense, right? Digital logic, input should be connected. Output not connected, that's okay. Output, I don't want to connect any device, that's okay, right? So it is offering, right? You know what is this signal is? That is by looking at this XC, AXI, ACLK. The clock frequency, bus clock signal. Amba, right? Amba bus clock XC, ACLK is bus clock, right? So all the signals are supposed to be working. Look at this, expanded. All these signals, right? All these signals supposed to be operating based on this clock, right? So something like address, right? Which one? Where is address? Oh, where is that? Write address, for example, right? This one. The write address. So write address. So that means right? PS is trying to write data to some IO device or memory, right? Then you are supposed to generate, right? Which memory location? 1000, for example, right? So that is operating based on that clock edge. The rising edge of the clock, that will be derived, right? So ACLK, bus clock, right? So you have to have that, that you have to have that input connected. Then is operating, right? Okay, let me, yeah, so GP master connection. So, okay, connect, do whatever you want to do, right? Okay, that is connected. If you click this, then clock, right? Bus clock is connected from this one, FCLK. PS is generating clock output that is supplied to all clocks, all clock inputs. Right? Clock output. That clock output, what is the clock output? You can open. Okay, clock, right? PL clock, right? This one, PL clock, right? PL fabric clock. Okay, I enabled only first one. Okay, so you can enable, right? You can enable this one, this one, this one. So inside PS device, PS module, you have a PLL, page page phase locked loop. So you can generate the clock frequency of your own, right? So 50 megahertz, 25 megahertz, you can specify. So there's one. Okay. Okay. Then take a look at this. Take a look at memory area tool assigned, Vivado assigned to this GPIO 8120, right? So according to that table, we just connected our GPIO to this GP1 master port. Right? So tool Vivado assigned small area within this within this memory region. Right? So memory map essentially memory map. It is creating memory map. Also, if you want, you can change, right? If you don't like that memory area, then you can change, right? Okay, I don't like it. I want it to be 30. That's okay, right? You can change the base location. And in this case, probably you don't have to have two connections, right? GP0, GP1. You can just remove, right? Why don't you open? Why do you open GP0 connection? Given that you don't use that connection, you don't use that output, right? So you can turn off that connection in this simple hardware system. Okay, any question about this? Okay, I think we are going to go through several labs. For now, don't worry too much about this one, GPIO and these things. I'll show you a demo with the board, and we are going to write some software as well. Okay. This lecture is still introductory. This PowerPoint is still introductory lecture. All right. Okay, so let's keep talking about this PS, the major component in the PS section. Right. So now it's APU. Okay, APU. Let's move on. Okay, APU. This one, Guyun, can you please?
Cortex M9 MP core V3 version 7 Neon 128-bit CMD coprocessor, 32 kilobyte L1I cache and 32 kilobyte L1D cache, 512 kilobyte shared L2. Snoop control unit SCU maintains coherency between L1D and L2. One-chip memory OCM, 256 kilobyte on-chip SRAM accessible by CPUs, PL, and central interconnect. 128 kilobyte boot ROM, not user visible. Zynq 7000 PTRM P678. Accelerator coherence port ACP from PL to PS can access the L2 and the OCM. Transactions are data coherent with L1 and L2 cache.
Okay, thanks. Cortex MP core, right? 2 CPUs. You have 2 CPUs. Version 7. Essentially, version 7 32-bit architecture. Right? Version 8 is 64-bit, right? Version 8. Smartphone is using version 8, right? Version 7 is a little old, right? Roughly 10 years old. And Neon, single instruction, multiple data with one addition instruction, for example. You can process, 4 different data. Okay, one instruction, 4 different data, 8 different data, and so on, right? SIMD, right? Single instruction, multiple data. And we have caches, 32 KB each for instruction and data. Associativity is 4-way set associative. Okay, L1 cache. So cache, if you look at this block diagram, cache is located inside this, Cortex A9. So L1 cache and another L1 cache here. And we have L2 cache located outside of this Cortex, right? Cortex. So size of L2, 512. So if I draw block diagram, it looks like this. You have Cortex A9, right? L1 data cache. Let me draw data cache only. Data cache. And 4-way set associative, 4-way. Then you have L2. L2 5, 12 kilobyte. I think it is 8-way set associative cache. So unified cache. Meaning data and instruction can be stored, here. Also shared, right? These two guys are trying to access this L2. Then we have some problem, right? This one is shared and L1 is private, right? So we have some coherency problem, a cache coherency problem, right? Maintain. Well, who is that, 경철? Who is that guy? Okay. So we have, coherency problem, right? So if you take advanced computer architecture course, the multiprocessor system, you have to think about coherency, problem, right? So a simple example is if it is a write back cache, okay, write back cache, then what would happen? So CPU update only this, cache line, okay, only this cache line to maybe 10. Okay, then what if this guy is trying to access, same location, same memory location. This guy is holding then it is generating, transaction to L2. Then if you don't do anything, you end up accessing this data, okay, this data, okay, same memory location, this data or from main memory, right? So from main memory. So this is the latest one, but you are accessing the old data. So we have coherence problem, right? So to maintain coherency, you have here in the middle between these two CPU and L2, you have SCU, Snoop control unit. Right? So things is a little bit complicated because you have separate connection. If you think about traditional shared bus based computer multiprocessor system, this is shared bus, right? And you have a processor P0, P1. You have cache, private cache, right? Cache, and memory is here, right? Memory. This is traditional, right? Multiprocessor system, simplified multiprocessor system block diagram. Right? Then the thing is very simple, right? So it's a private cache. So if this guy is generating some transaction, CPU, then data is not found here, then you are generating bus transaction. And shared bus, that means this transaction can be seen because it's shared, right? Connection. This transaction can be seen by this guy, also this guy. So this guy can respond. Okay, this guy says, okay, I'm holding the latest data. So you have to get data from me. So it is providing data like this, right? But in this case, in our case, it is not bus based, right? So you have this connection. You have separate connection, right? So here you have SCU, Snoop control unit, and you have L2. So it is making, it is generating transaction, and go through L2. The transaction, this transaction, CPU generate, cannot be seen by this guy. This guy cannot see the transaction, right? So you have to design some special hardware, okay, to make sure the coherence is not broken, okay? So you have, let me show you. Okay, let's talk first about this SCU. You have SCU, okay? So CPU, two CPUs, okay, here, two CPUs, and SCU, Snoop control unit, separate connection. First CPU to SCU, and the hidden, right? Hidden in the hidden box. From there here to, the request. Then L2 is located here. So it has some some memory, right, to store information about the caching information of this cache, the information about this cache, So this guy should have some information about the status of the memory block, right? This memory block, the memory block, many memory blocks are stored, right? So this guy should have some information. It should keep track of the status of this guy, this memory blocks, right? So let's read this first. This one, Dongwon, can you please?
Snoop control unit is responsible for maintaining L1 cache coherence between two processors. SGU supports the MESI snooping. It has four-way associative tag lengths, acting as a local directory that leads to coherent cache lines held in L1 data cache. A local directory allows the SGU to check if data is in the L1 data cache. so accesses can be filtered only to the processor that is sharing the data. L1 data caches are four ways that associate with write back, write allocation, and MESI.
Okay, so if you are not familiar with those terminologies, okay, so write back, write allocation, write back, write allocation, messy, then I recommend my book. Okay, I recommend my book to you. I recently wrote undergrad computer architecture textbook, right? This one has I think I try to write the book in a very easy language, with a very easy language. If you scroll it down, the last chapter is about multi-core processor. So it is talking about cache coherence protocol with example, program example, not just theory, not program example. Okay, and also cache. It is talking about write back, write allocation, those policies. Here, so it says for cache coherence, they implemented this messy protocol. It is the most processor is using messy as a base protocol, messy. Some processors like Intel is adding one more state to messy. They call it MESIF. And AMD used to use MOESI, okay, on one more state, okay, but it is based on messy MESI, right? So MESI protocol is used as a base, and some processors use some variant of that processor, the protocol. SCU has a local directory, right? Tagram to keep track of memory blocks. These guys are caching, right? So otherwise, the SCU, this guy, CPU generate transaction. Otherwise, SCU cannot tell. It cannot tell. Generate transaction, SCU doesn't know, right? If you don't have tagram, right? Tagram, then this guy does not know the status of this guy. Then transaction will be forwarded to here or main memory, right? So should keep track of some information. Then what else? So it says the spec says L1 data cache. Write back, write allocation, write back cache, meaning you are updating. In case of write transaction, store transaction, memory write transaction, you are updating only cache, not memory. So that is a little bit that is not clear, because right, if it is write back, then what would be the problem? SCU, it is touching only L1 cache. Okay, it is dirty line, right? Dirty. Okay, it is updated. Then that information is not reflected in tagram. Then this guy is generating read transaction, memory read transaction, right? Then what happens? Then it is not accessing this data, right? So we have some problem. So that means the spec does not say in detail that that SCU does not say anything about this tag RAM management. But my guess is, my guesstimation is, when you update L1, I think some hint information, that update information should be delivered to this SCU, so that tag RAM keep the latest information, okay, this update information. Otherwise, right, this guy read, then that information is not going to be, data is not going to be requested, right, to this L1. So my thinking is some kind of hint transaction should be generated, even though it is write back, right? That is my guess. Okay. Okay, some detailed management management mechanism is not disclosed. Just they say this diagram. Okay, keep track of. Okay, that is about SCU. But in our class, I don't think we are going to turn on 2 CPUs. We are going to use only 1 CPU. Okay, so probably don't have to worry about this cache coherence protocol. Okay, then on-chip memory. So inside APU, we have a very small internal memory, on-chip internal memory. So 256. And the spec says it has one additional memory called boot ROM, 128 kilobyte boot ROM. But this block diagram does not show the where boot ROM is located. I think it is hidden, and the spec says it is not user visible. You cannot access it, right? So I think that is used in the in booting time. You turn on Zynq device, then the information, some instruction, I don't know, that will be used to initialize device, some configuration, right? I don't know, they don't disclose the information. You can find out that that statement in Zynq 7000 TRM technical reference manual page, this page. Okay. And we have ACP port. Where is Himin? Himin is here. Oh, okay. Himin, okay. Himin will get a shot today, vaccine. Okay. And so Himin and Sangwon is expert in ACP. My student, Sangwon is expert. He's playing with this ACP port. Okay, ACP means what? Which one? Okay, here. From PL section. Let me go back. Show you the full picture here. So here, ACP. So from PL, this gray, your custom logic. Custom logic can generate transaction. Okay, can generate transaction through that connection that is connected to SCU, Snoop control unit. That means your custom logic can access some memory location which is shared by the CPU. CPU access some memory location and your custom logic access the same memory location. Then data coherency should be maintained, right? So that is guaranteed. That is guaranteed by SCU. Okay? So there are 3 parties. Okay, 3 parties involved in 3 parties involved, right? Master component, your 2 CPUs and your custom master component can share the same information, right? Okay, that is the one. So from PL, your custom logic to PS, right? Your custom logic to PS can access level 2 cache because SCU to access level 2. To access level 2, you have to go through, right? So we have here, we have ACP port, PL section, right? So you are generating transaction, so you can access L2, okay? L2, and on-chip memory, depending on the address you are generating. So you can access, on-chip memory, okay? And SCU will guarantee, okay? Data will be coherent, okay? So this is the one we already did. Any question about this, by the way? All right. Okay, so these arrows, So master to slave component, right? Master to slave component. On-chip memory, connection to on-chip memory, connection to master to slave, right? SCU, connection to L2, level 2 cache. Okay. Then if you have data is found, instruction is found in L2, then this guy can give you. Not found, then DDR or IO devices, system interconnect. Main memory, IO devices are connected, right? Depending on memory, memory address you generate. Okay, so okay, this one, Dong, can you please?
All accesses through L2 cache controller can be routed to the DDR or other slaves in the PS or PL, depending on their addresses.
Right. So depending on the address CPU generate, okay, access can go to DDR, final OCM or DDR or IO devices through this system interconnect. Right? Internal memory, external memory, and IO devices, depending on address. Right? Okay, so SCU, let's simply read and move on. This one, Jinwook, can you please?
The Snoop control unit connects to Cortex-A9 processors to the system memory peripherals via XC interfaces in Zynq 7000 EPP, provides L1 data cache coherence between the Cortex-A9 processors, arbitrages between Cortex-A9 processors requiring L2 cache accesses, provides access to the on-chip ROM and RAM, manages accelerator coherence for ACP accesses.
Okay, so the first sublet, L1 data, right? Level 1 data cache, coherency, okay, is maintained by SCU because it has local tag RAM, and arbitration to L2, right? Because what if two guys are requesting transaction at the same time? Then SCU is doing arbitration. Okay, you go first. You access L2 first, right? You go next, arbitration, right? Because you have only one connection to L2, right? Arbitration. Provide on-chip ROM and RAM, right? On-chip boot ROM, right? Boot ROM and on-chip internal memory, right? OCM, right? Provide access, right? Here, this one, this connection. Okay, and manage ACP port, right? So ACP, here from PL to your custom logic to that connection. Okay. Okay, let's move on. Okay, L2. Too much detail probably. Let's read anyway. This one, Jihoon, can you please?
L2 cache controller. High performance L2 cache controller. 12 kilobyte of cache support lockdown by line for routines that might need low latency. 8-way set associative parity support, write-through and write-back support. L2 cache controller XC interfaces. One XC master interface for the DDR controller. One XC master interface for all slaves devices in the PL and PS. One XC slave interface for the loop for the Snoop control unit.
See, slave interface. Okay, yeah, right. So L2, right? L2 cache controller. You have a level 2 cache, right? Then you should have a level 2 cache controller, right? Cache controller is controlling, right? L2 cache controller. Right? You have to, read the data from this memory cache and write to, right? Read and write. So you have a cache controller. Support lockdown by line for routines that might need low latency. And typical cache, cache contents are managed by hardware automatically, right? You don't have any control. So sometimes this memory block, okay, this line may be kicked out, okay, to bring in new memory block. But if you need that memory block cache it all the time, then you can lock down that cache line, okay, by program. I think I haven't tried that before, but the spec says you can lock. Okay, I don't want to kick out this guy. Okay, do not kick out the specific cache line. Parity support for that the check, okay, the data integrity, okay, write through, write back support, right? Write back policy or write through policy. You can select by software. L2 cache controller, we can I think we can move on. Okay, ACP. This one, I think, Sangwon, can you explain? You are expert, right? Can you read? And
ACP, Accelerator Coherency Port. The Accelerator Coherency Port is a slave AXI 64-bit port on the SCU connected to the PL under 50 MHz in one device. ACP port can be used by accelerators in the PL to access the ARM L1, L2 caches and maintain coherency. Cache accesses could be used as a means to share data between the A9 CPUs and hardware accelerator in the PL with low latency.
okay, and explain. You are expert,
Yeah.
right?
ACP. ACP it is connected to SCU, so it is fast than other port, which is connected to the usually the memory. And also it is connected to SCU, so it make currency with L1 and L2 caches. As it says, it is mostly used applied to the machine learning technique. So
machine learning? What do you mean by that? Machine learning technique?
I mean the accelerator, machine learning accelerator.
Oh, okay.
I
You are
guess.
assuming machine learning accelerator is located here. Machine learning accelerator.
Many, I guess it is really good to use ACP port.
For machine learning?
Isn't it? I'm not sure. Actually.
Machine learning, I don't know. For machine learning, think about CNN, right? Convolutional neural network for image classification. That means you need a lot of data. Machine learning, I think Guyon is expert, right? Guyon, can you comment? You are expert, right, in machine learning. CNN accelerator.
Yeah, I'm not sure, but maybe ACP can helpful to control. I'm not sure.
Yeah. So if you think about CNN, you need a lot of data, right? Weight, right? And weight, right? Weight and input, intermediate data. Okay. So if you add CNN accelerator here, then get data, right? That get weight from ACP. I don't know. This ARM CPU, ARM processor is accessing that weight, and this guy also accessing that weight and input data. You maintain coherency among these three guys. I don't. That is not typical scenario, right? You don't have to share. You don't have to share weight and input data. between accelerator and CPU. That is my guess. Right? Accelerator, you need only the data, right? Input data and wait. You don't have to share that data with CPU. It is doing some control management work, I think. And main task, main convolutional task, and what the fully connected, right? That task should be performed by this, hardware accelerator, right? So that means you are just reading, right? Just reading data, okay? Reading data. You don't have to maintain coherence between these two guys, right? That is my guess. I don't know. Okay, anyway. Okay, thanks. Anyway, look at this. This connection, 64-bit. 64-bit connection, data bus. And then maintain coherency, okay, between L1 and L2. Right? So it is injecting some transaction. That means SCU is taking care of the data coherency, right? Taking care of data coherency, which need for L1, L2, L1s, and where is L2? L2 here. L1 inside processor, right? L1 inside here, and L2, right? Injecting transaction, right? Okay, let's move on. This one is Amba, right? Probably you have, it's good to know. It's good to know about Amba protocol because it is almost universally used in the industry. When you build SoC, system on chip, go to Samsung, LG, right? And SK Hynix. If you use ARM or other CPU, other processors also use that protocol because it's just interconnection protocol. Let's read first, then move on. This one, Kyungcheol, can you please?
The advanced microcontroller bus architecture is used as the on-chip bus and system-on-a-chip designs. Amba was introduced by ARM in 1996. Xc, Advanced Extensible Interface, AHB, Advanced High Performance Bus, APB, Advanced Peripheral Bus, ATB, Advanced Trace Bus.
Okay, so if you search with Amba specification, okay, then this one. Okay, overview first. So it says Amba stands for Advanced Microcontroller Bus Architecture. It is freely available, it says, freely available and open architecture for connection and management of IPs, hardware IPs, functional blocks, hardware modules in SoC, system on chip. Okay, so it says Amba specification is royalty free, and platform independent, can be used by any other architectures. So probably, not only ARM, RISC-V, right? If you are interested in RISC-V CPU, then you can use that interconnection protocol to connect, memory and IO devices, right? So again, Amba is so popular. The reason why it is popular is because ARM is so popular. Almost everyone, right? 99% of embedded system designers use that Amba, protocol. Okay, that is why all the IPs, almost all the IPs are designed with Amba interconnect. Okay, you have interconnection, right? Some IO device. Assume that you are designing some special hardware component, some IO component, right? IO component, then you should have interface, right? That is based on probably Xc, right? Xc4, okay, interconnect. Then that hardware module can be plugged into plug and play, right? Like plug and play. You just plug that hardware component into some SoC. Then it's seamlessly integrated into that chip. Because connection, okay? The other modules understand this connection, right? So it is like it's very widely used. So good to know about this, connection, right? So it has a long history, right? So according to this one, from 1996. 1996? I worked for LG 1995. At that time I used Amba. No, I don't know. My memory is a little old. 1996, that means 25 years ago, right? 25 years ago. And at that time I played with APB and AHB, that bus interface. So go to this specification, okay, tab. Then Amba 5 is the latest, and Amba 4 is one generation behind, and so on, right? And our Zynq device is using, I think, these two, Amba 3 and Amba 4, according to the document, Zynq document. Okay, so you can check out the protocol, okay, here, and also on our class page, I created this link. This is a little bit old. I cooked up that document, I think 7 years ago, something like that. So look at this document, little introduction about Amba. Okay? So Amba, first one, ASB and APB. Okay? HB, I was using, I was playing with ASB and APB, okay, AHB, those things, okay, and so on. So I think we will have some time to explain about a little bit detailed protocol. Okay, how master device, CPU, for example, communicate with I/O, slave device. This is one example. Okay? So I took this from wiki page this morning. So I will have a chance to look at this. Okay. Okay. So Amba, right? Amba protocol. And if you look at this block diagram, look at this. Here we have some legend. Okay, color coded. XC32 interface, 64-bit, green. Okay, dark green. Where is that? Dark green. This one? Dark green connection. Is it green? Confusing. Is it green? No, not green. Which is green? Dark green. I feel like I color blind. Looks green. I don't know. Is it green? Oh, okay. Very confusing. Okay. I don't know. This bluish, light bluish. Where is the one? Bluish XC connection. This one, 64-bit, right? 64-bit connection. I think this one should be 64-bit connection, and this one too, because it goes through memory, right? 64 memory should be 64-bit, right? And it has AHB, pretty old bus protocol. AHB, purple, this one purple connection, AHB, and APB means H means high performance. At that time, very old, but high performance bus, advanced high performance bus. APB means advanced peripheral bus, I/O, right? Connecting I/Os, right? Like this one. I/O doesn't have to be fast. This connection doesn't have to be that fast, because I/O is already very slow, right? So you don't have to have fast interconnect. That's why it is using APB. So Zynq device, Zynq has XC, AHB, and APB protocol implemented in PS section. Okay, so interconnection. Okay, in the demo, I showed you this one, right? XC, right? This one is XC Lite connection, I think. This one XC. Expanded. Yeah, XC4. XC4 some detailed signals, okay, in detailed signals like address, data, some control signals, right? In this, this slave connection. Then, okay, PowerPoint. So if you look at this high level explanation of Xe, does it have Xe? No. Okay, probably website. Here. Overview. No big. 4. Okay, so if can you read this one? Okay, Xe4. Okay, inside this box, Xe4. Underneath is Xe4 light, right? Light stream. So Xe4 is providing 3 kinds of protocol: Xe4, Xe light, and the last one Xe stream. Xe light. Light means like Xe light is used to connect. As the name implies, light, right? It is used to connect, slow I/O devices. Okay. So I think this one is Xe light. This one is Xe light. This is using Xe light connection protocol. Okay. Okay. PS to PL. Okay. PS to PL. PS to PL to PS. PL to PS. Okay. This one. Okay, Sungwon, can you please?
PL uses 4 high-performance Xe ports to access the PS memory. Each Xe port from PL can be configured for 32-bit or 64-bit operation. 150 MHz operation in A-1 speed grade part. Xe FIFO interfaces are large FIFOs to smooth large data transfers. Clock domain crossing between the PL and PS is managed in the PS.
Okay, sometimes from this PL, your custom logic. Okay, your custom logic can be used as a master component. Okay, your master component can access PS memory. Right? Through this DDR. Right? Then the problem is the clock frequency would be different, right? Your custom logic clock and PS clock may be different. Okay, to close that disparity, to reduce that impact, you have this FIFO, okay, Xe FIFO interface, some buffer essentially, right? Buffer, okay? This big buffer. Okay, so the transaction data is accumulated. Okay, the data is pushed to this FIFO, and then the output side data will be passed to this switch. So some internal block diagram. Okay, PS2PL export. PS2PL, PS2PL. I think we did that, right? To master. PS2PL. Okay, PL2 PS, right? PL. It is talking about this 4 PL2 PS, PL2 PS, and PS2 PL. At the beginning of this class, I showed you demo, right? PS2 PL. This PL, PS2 PL. Okay. Let's move on. Okay, and also it has a DMA engine inside. If you go to this page, inside APU, you have DMA engine. Okay, DMA engine integrated. So with the DMA engine, you can do DMA transfer like this. Typical DMA transfer occur between memory to memory, like this one, orange, arrow, from this on-chip memory to external memory, internal memory to external memory, and memory to I/O devices, the green one. Okay, probably your custom logic. Inside your custom logic, you have some buffer, 1 kilobyte buffer. You want to transfer this data to this external memory. You can use the DMA, right? Direct memory access. Okay, so let's skip this. I think I showed you briefly about this clock, okay, in the demo. Let's move on. Okay, skip this part. And the board we are going to use. Guyun, can you, how many of you need the board? I think 동우, 경철, right? 동원, 승훈. 진욱, do you have the board, that board?
Yes, I have.
Okay. Then 지훈, 지현, 훈종. 7. We need 7 board, okay? Can you prepare 7 Zedboard package? The package should include, yeah, and please pick up your board, okay? 구윤's office is located at 애기능 생활관 307. Okay? 애기능 생활관 307. Okay. Probably what would be good? 구윤, they have to make an appointment to you, or what would be good?
제가 10시 이후로는 웬만하면 연구실에 있으니까 그냥 아무 때나 혹시
Anytime? Sure.
내일 중으로 오시면 될 것 같습니다.
Probably you can set the time slot. Probably from tomorrow, from 2 p.m. to, I don't know, 2 p.m. to 4 p.m.
네네, 내일
Tomorrow is
오후
Friday.
내일 금요일입니다.
Is it okay? 2 p.m. to 4 p.m.
예, 저는 괜찮습니다.
So during this time slot, probably you can visit this office, then pick up your board. Right? Otherwise, right, then you have to keep waiting, right? It is not good. Okay, so the Zedboard package, Zedboard package
예,
should include Zedboard, right? Zedboard and camera, right?
예,
CV OV 7670, right? Camera, okay?
네, 알겠습니다.
This one, this camera, okay? That camera, very cheap. I think, how much is that? This camera is 1,000
4달러입니다.
4달러?
네.
4달러. Okay. Then this connector. Okay. Then wire. And this wire, right?
네.
This wire to connect to the Zedboard, right? And USB cables. 2 USB cables plus 2 USB cables. Is it? For downloading hardware and what? And UART connection. So that should be included. Okay. Okay. So little introduction about Zedboard, right? So we have Zynq device, Zynq 7000, and then memory, right? External memory, 512 megabyte, and UART connection. The shape is USB, but its function is UART. Serial communication, right? So inside the Zynq device, we have what? Inside Zynq, we have UART, right? UART, this one. So CPU, sometimes in the PS, this guy want to send message to PC, your PC, right? And that message will be sent through that connection, right? So is again inside this Zynq device, you have UART. And if you program that UART, then that message, right? The message will be passed through that connection. So that this one is connected to your PC, And this one is for downloading your bit stream. After you design this hardware, synthesize it. The synthesis, we call that synthesis, right? In hardware world, you have to go through synthesis. Is it right? SYS? I don't know. Synthesis, okay? HDL or schematic based design. Synthesis, then you are generating this, logic. Okay, this kind of logic, synthesis. Okay, after tool will synthesize the logic, then that will be downloaded through that connection. Okay, that connection to this here, and we have HDMI transmitter. Okay, so you can connect your HDMI monitor through that connection. Okay, and then we have on the flip side, back side of the board, we have clock. Okay, PS clock, 33 megahertz input clock, input PS, right? PS is taking that clock and generating some output clocks. Because internally you have PLL, right? Internally you have PLL. And also another clock source, 100 megahertz, okay, that is used to drive PL. So you can use PL, right? If I draw a little block diagram, it looks like this. You have PS, PL in Zynq, and clock, right? 33 megahertz. That is driving PS, right? And PL, you have one more clock source, 100 megahertz. Okay, and also PL can be can use the clock sources generated from this PS, okay, like FCLK one. So I showed you, right, something, right? So PS can generate, taking this one as an input, phase locked loop can generate this output. So PL can use either this one or that one. Okay, your digital logic. Then we have some audio codec, right? Coder, decoder, and so on. Okay. Okay, what time? Okay, 13. Okay. This one is a Zedboard, not Zynq, right? The Zedboard block diagram, right? You have a Zynq device, this device. Look at this. This one Zynq, not only Zynq, you have many hardware component mounted, right? Like what? Switch, right? Switch and LEDs. Right? So look at this diagram. You have a Zynq, you have switches and LEDs connected, right? And those switches and LEDs are already connected to PL here. Okay, PL. So to control these switches and LEDs, you have to have some hardware logic, your custom logic located here. Right? So if you want to use HDMI monitor, then you have to place some hardware component that is interacting with that HDMI controller. You should have something, right? You should have something to drive a VGA monitor, right? Should have something to control LED, so on, right? That is a rough block diagram. Okay, and okay, I think we can stop here. That is everything I have. From next class, we are going to do the lab. Okay, so check out this schedule. We will do the lab from next class. Those 4 labs, those labs. I'll show you some demo. Okay, then ask you to do some homework. Okay, after each lab. Okay. Okay. Any question? Okay, that's it. See you. See you next time. Have a nice Thanksgiving. Okay, thanks.